In Unit 7, we'll be learning about momentum and impulse. Momentum is another new quantity that has a lot of applications. For instance, we can use it to study collisions like car crashes, and we can begin to understand what factors influence the risk of injury when you're in a car crash. We can also study rocket motion, how rockets work. We can look at recoil when you launch a projectile, fire a gun, that kind of thing. And this has applications in sports too, like if you're hitting a golf ball or baseball or tennis. And like with energy, there's a conservation law for momentum. Momentum is a conserved quantity. So the law of conservation of momentum will become really useful when we study these kinds of examples. So let's get started with our definitions of momentum and impulse and look at some applications and some examples. So first of all, momentum is defined as mass times velocity. We use the symbol P for momentum because m is already taken by mass. So momentum P equals mass times velocity. Now let's notice a few things about this definition. There are only two factors that influence momentum, mass and velocity. So the greater an object's speed, the larger its magnitude of momentum, but also the greater the object's mass, the larger the magnitude of momentum. This is a vector equation, so momentum has a direction, and the direction of momentum is exactly the same as the direction of the velocity vector. Momentum essentially is just velocity scaled by the scalar factor m, the mass. So momentum, if you could write it in component form. Like so. And if it was 3 dimensions, there would be a z component as well. Momentum and kinetic energy are related. Kinetic energy is the magnitude of momentum squared divided by 2 times the mass. You can do a little algebra and see that this expression equals 1/2 mv squared. Now, momentum actually comes from Newton's second law. In fact, when Newton wrote Newton's second law originally, he used momentum. So I'll show you the form of Newton's second law that Newton used that's going to be handy for understanding collisions and things like that. So here's Newton's second law. We know Newton's second law as the sum of the forces, or the net force, on an object equals mass times acceleration. In our kinematics unit, we learned that acceleration is the change in velocity divided by the change in time. Now, if we group mass and velocity together, we can write that as the change in mass times velocity divided by the change in time. And actually going from this step backwards to that step is not totally straightforward, because this does imply that mass could change. And in fact, that's what happens in rocket motion. For now, we'll assume that mass is constant in all the examples we analyze. So delta mv means m delta v. But later when we do rocket motion, delta mv means m delta v plus v delta m. So now we've learned this definition, momentum, and this equation becomes change in momentum over change in time. And that's another way of expressing Newton's second law. It's totally equivalent. And in fact, more general. All right, so let's define another quantity. Let's multiply both sides of Newton's second law by delta t. So we have F net times delta t. And we're going to call this thing the impulse, symbolized with capital I. And written this way, Newton's second law is known as the impulse-momentum theorem. The impulse applied to an object equals its change in momentum. That's really just Newton's second law in disguise. But we give it this name because it's kind of symmetrical with the work-energy theorem that we learned about in the previous unit. It says that when you do work on an object, its kinetic energy changes. Now we say when you apply an impulse to an object, its momentum changes. So essentially these are two different ways of saying if you push on something, its motion changes. Work energy theorem, impulse momentum theorem. Put very simply, if you push on something, its motion changes. But we have two different mathematical formulations of that intuitive statement. So this one is useful for certain types of situations, for some collisions. Let me just remind you that since impulse is force times delta t, we can replace the left side with that, and momentum is mv, so we can write mv final minus mv initial. In real life, when forces are applied to an object, they're rarely a constant value. That's especially true in collisions and the types of things we're analyzing in this chapter. Typically, in a collision, what will happen is that the objects start to touch and they begin to apply forces to one another, and that force keeps increasing as they collide more strongly. And then when they bounce off each other, that force decreases. So if you plotted the magnitude of the force versus time, it might look something like that. Objects that just begin to touch, and now they're really smashing against each other. You have the highest value of the force there, and then they begin to move apart and the force decreases. So that might be some fairly complicated function of time, but when we analyze these problems, we can typically replace that behavior with just the average force applied to an object. That's because the important quantity is really the area under this curve. So if we find the average value of force and use that average value over the duration of the collision, then this area is the same as that area. And we just have to deal with a constant force, with an average horizontal force. I mean, an average force that looks like a horizontal line on this graph. When you do physics with calculus, then you can worry about the full function versus time. Okay, let's do some examples. I've got two examples from the chapter, or from the section of the chapter. First example, 6.1, involves hitting a golf ball with a golf club. Okay, let's say that the golf ball has a mass of 5 times 10 to the minus 2 kilograms. That's 50 grams. And you hit it with a golf club, and the ball gets launched at a final speed of 44 meters per second. So let's answer two questions. Part A, find the impulse given to the golf ball. And part B, estimate the time of collision and the average force on the ball. All right, so part A, we can analyze this using the impulse momentum theorem. It says that impulse equals change in momentum and in this problem we are given all these values the initial is 0. The ball is stationary when you hit it. So that goes away, and we've got just mv final 5 times 10 to the minus 2 kilograms, 44 meters per second. And that gives you an impulse equal to 2.2 kilograms times meters per second. The units of impulse, the units of momentum, are kilograms meters per second. You You can see that from the definition of momentum, mass times velocity. And we don't have any special name for this, just kilograms meters per second. Now part B, let's estimate the time of collision and then use that to figure out the average force. So in your textbook they say, well, let's estimate the time of collision as the distance traveled during the collision divided by the average speed during the collision. And they kind of invent some values to put in here. They say the distance of the collision is about the length or the diameter of the golf ball, which is 2 centimeters. And the average speed during that collision is half of the final speed. It's a reasonable assumption. So half of 44, 22 meters per second. Okay, we can estimate the time of collision as the distance of the collision divided by the average speed, and your textbook tells you to estimate this as the distance of collision being the diameter of the golf ball, which is about 2 centimeters, and the average speed of the collision being half the final speed. So we'll take half of 44 and use 22 meters per second. And that gives us a time of collision roughly equal to 9.1 times 10 to the minus 4 seconds. Now that we have that, we can estimate the average force. Which is the change in momentum over time. We already figured out our change in momentum, or the impulse. And plugging in those values, 2.2 kilograms meters per second over 9.1 times 10 to the minus 4 seconds, we get an average force of 2,400 newtons. So that's the first kind of collision we've been able to analyze, a golf club meeting a golf ball. Now let's look at a car crash. This is example 6.2 from your textbook. In this example, we have a car of mass 1,500 kilograms that collides with a wall. So initially it's going to the left towards that wall at 15 meters per second. Then it smashes into the wall and rebounds a little bit. There's our smashed car. And it rebounds. V final is positive 2.6 meters per second. And we're told that this collision lasts for 0.15 seconds. So let's find the impulse and the average force applied to the car. We're going to find that it's a very large value of force. So the impulse is the change in momentum, mv final minus mv initial, And we just need to keep careful track of the positive and negative signs. V final is positive, the car is rebounded and going to the right. So we have positive 2.6 meters per second. And then we subtract the initial momentum, keeping in mind that that initial momentum is negative. So we get two negative signs, they end up giving us a positive number. So that impulse is 2.64 times 10 to the 4 kilograms meters per second. And we find the average force by dividing that impulse or change in momentum by the time of collision, which was 0.15 seconds. And that gives us 176,000 newtons of force. Now that's a really large value, and that's why car crashes are dangerous. In the next section, we're going to analyze what factors influence your risk of injury in a collision.